Okay, does anyone have any questions for me before we begin today? All right. So today is going to be, the lecture topic is conditional probability, which we'll define soon. And this lecture and a few of the upcoming lectures will have a similar theme. And that theme is that there'll be some concept. Today it's conditional probability. Next time it might be independence that we will define. So it'll have some mathematical definition, but it'll also have some intuitive definition. And we'll look at the mathematical definition on a few examples and see that indeed the mathematical definition agrees with our intuitive definition, so that this really is the notion that we think that we defined it correctly, so it is the thing that we thought it should be. But then these classes will often end with an example in which the mathematical definition really diverges from what you expected. And the reason for that is not that the mathematical definition was wrong, it's that actually your expectations were wrong. The mathematical definition really does agree with some real-world experiment that we would do that would have some probabilities of various outcomes. But your understanding of that experiment, you'll see, was probably incorrect just from looking at it, and it's not until really analyzing it very carefully this way that you realize, well, what your misunderstanding was, or at least that you had a misunderstanding. So we'll start today, before we jump into the definitions, we'll start with this toy problem that some of you may or may not have seen before. It's called the Monte problem, or the Monte dilemma. It goes back to an old game show called Let's Make a Deal. So it was a TV game show. And at some point in the game, it's sort of like the grand finale, there's a situation where there are 3 doors. Each one opens into a different room. And what you know is that behind 2 of these doors, there are goats. And behind the other one is a fancy sports car, usually a red one. And we'll assume that you would rather have a sports car than a goat. So whether that's a valid assumption or not, that's the assumption. A goat can feed you for a long time, a sports car not so much. But we'll say that you would prefer a sports car to a goat. So you're going to win if you manage to get the sports car. And then the game plays out like this. You pick one of the doors, and you say, I'm picking this door right now. So you pick it at random. There's 3 doors, so with probability 1/3 you pick with this one, with probability 1/3 you pick this one, and probability 1/3 you pick this one. And you tell the game show host, Monte Hall, this is the door that I pick. And then the next thing that happens is always the same. Monte takes one of these 2 doors and opens it. And it's always the same story. He shows you a goat-like animal that looks like that. Okay. So Monte is always able to do that because there are 2 doors that you didn't pick, and there's only 1 sports car, so definitely one of these things has a goat behind it, and he opens, if there's only 1 with a goat behind it, he opens that one. If there's 2 with goats behind them, then he opens either one. But it always plays out the same way. He never opens the door and shows you a sports car. All right? And now Monte says, this is your final decision. Would you like to keep the door that you picked, or would you like to switch and take what's behind the other door? In either case, the door is going to open and you're going to get what's behind your final selection. So the obvious question is, well, what's the best strategy for you to play this game? I mean, so far, there's only one choice, and the choice is what you should do in this last step. Because the game always plays out the same way until this last step. So let's think, there's 3 doors. So I don't know, maybe, and there's only one sports car. So like a reasonable thing you might hope is like maybe a good strategy should at least get you winning the sports car half the time. So what's the strategy if you want to win the sports car half the time? Yeah? Yeah. So at this point, you flip a coin and you take this door or this door, depending on the outcome of the coin, heads or tails. Yep. We won't really use the probability tree. No, we'll just use an observation. So at this point, you know the situation. There's a car behind one of the 2 doors. There's a goat behind the other. If I toss a coin, then to decide which door to open, then half the time that coin will give me the car. The other half of the time it will give me the goat. So I can win this game with probability 50% or with probability 1/2. Can I do better?
Yes.
Yep.
You can switch.
You can switch.
Give you a slightly higher chance because you know that there's one sports car and 2 goats behind the 3 doors. And since Monte opens one of them, he eliminates one of the options.
Okay. So the proposal is that at this point we should switch our guess always, and that should give you maybe a bit better than 50% of the 50% chance of winning. Who thinks that that's true? Okay. And who thinks that that's crazy? So it turns out to be true, except for the part about slightly better than 50%. It's actually a lot better than 50%. And the way to see it is the following. So here is a probability space, which is basically the space determines your first choice. Okay. So you remember I said the first thing you do is you pick one of these 3 things at random. And you don't open the door, but there is something behind that door. You just don't know what it is yet. So when you make this choice, there are, well, let's do it the easiest way. There's 3 things that could happen. You manage to pick the door with the car, you manage to pick the door with goat number 1 behind it, or you manage to pick the door with goat number 2 behind it. So you guess the door with the car, or you guess the door with goat number 1, or you guess the door with goat number 2. That's the probability, the set of possible outcomes for when you make that first choice. Okay? And what's the probability that that first choice you pick the car? Yeah. And what's the probability that you pick goat number 1? A third. And the probability that you pick goat number 2 is also a third. So that's a uniform space. So let me just write it more generally. The probability of any particular outcome is equal to 1/3 for each outcome in each of those 3 possible outcomes. All right. Now, let's define A as you picked the door with the car. Then we've just argued that the probability of A is 1/3. And what is the probability of not A? So not picking the door with the car. So it's 1 minus the probability of A, that's the complement rule. So it's 2/3. Now we're considering the strategy where whatever happens, you pick this thing, and now whatever happens, Monte opens something, and you switch. So how could you lose? In that strategy, how would you lose? Yeah. If this first choice that I made was the door with the car behind it, then when I switch, I'm going to lose.
So you pick the right door.
So that means that I'll only lose with probability 1/3. And on the other hand, if the first choice that I made did not have the car behind it, then when I switch, I'm going to win. Which means the probability that I win using that strategy is this probability of not A, which is 2/3. So your chances jump from 50% to 66.666%. It's a substantial increase. And you know, if you're into gambling, these are like important things to understand, because these can really determine whether this is a game you. I mean, if there's bets on the line, this determines whether you want to play the game or not. Is that clear? Good. A lot of people struggle with this Monte Hall problem, and so it's good if I manage to explain the solution, or rather the winning probability with the switching strategy in a way that everyone is clear on what happens. But the short version of the story is you only lose if you happen to pick the car with that first random choice. And that only happens with probability 1/3. All right. Good? Yep. You have a bigger probability of, when you switch, you have a bigger probability of winning. Your probability of winning with the switching strategy is 2/3. Your probability of winning with the sticking with your first guess strategy is 1/3. Okay. All right. So now let's look at a word problem, and I'm going to do it over here. We'll work it out intuitively, and then we'll work it out, we'll define conditional probability and work it out the other way, the proper way, and then we'll save it for the end for when the surprise comes. So here's the thing. Anil has 2 children. So this somehow says, and what I'm interested in is the sexes of these 2 children, boy or girl. So this somehow says that there's an underlying set of possibilities, and that underlying set of possibilities looks like this. The first child is a boy, and the second child is a boy, or the first child is a girl, and the second child is a girl, or the first one is a boy, the second one is a girl, or the first one is a girl, and the second one is a boy. So that's, when you just read this statement, this is what you might think immediately. But then the next thing I'm going to tell you is that at least one of Anil's children is a boy. Okay. Now, before I told you that, this was the model of the situation. There were 4 possible outcomes, and each one we'll ignore a small issue in genetics, that when you have a child, it is equally likely to be a boy or a girl, with each one with probability 1/2, and that the sex of your firstborn child has no relationship to the sex of your second-born child, so that each of these 4 possible outcomes was equally likely before I made this second statement. So that means each of these had probability 1/4 of occurring. But now I've told you that at least one of Anil's children is a boy. So that rules out one of these possibilities. That rules out this girl-girl possibility. So let's call that B. And so that this is an event, right? So if this is a sample space of all the possible outcomes, this defines an event, and the event is 2 boys, a boy and a girl and a boy, but not included in that event is this outcome where it's 2 girls. Okay, and now the question is, given everything you know, what is the probability that both of Anil's children are boys? Okay. So already, just writing it down carefully like this gives us a hint about what the answer should be. But even before I wrote down this set B here, you might have thought, okay, so Anil has 2 children, at least one of them is a boy, and the question here is saying, well, what's the probability that the other one is a boy? So what would you think the answer to that should be? Yeah? Not the product. So if it was the product of the 2, then it would be 1/2 times 1/2, 1/4. But at least if you don't reason too carefully, you think, well, yeah, you told me the sex of one child, and now you're asking me about the sex of the other child. That should be 1/2, right? I mean, it should be that it's equal, that other child is equally likely to be a boy or a girl. That intuition is wrong. Why? Well, what you told me when you said that there's at least one boy, you told me that this set of 4 possible outcomes, they're not all possible anymore. There's actually 3 of them. And more than that, these 4 were equally likely, and actually, therefore, these 3 are equally likely. So the answer is that the probability of, so let's define A is this outcome, both of Anil's children are boys, which is just a 1-element set, a subset of the whole space, it's BB, and actually the probability of A is 1/3. And that's because each of these has probability 1/3, and this is exactly one of those things. So that's already weird. You're talking about, an experiment that was designed with the sex of a child in mind. Each sex occurs with probability 1/2. but somehow I told you something about the experiment, and suddenly one of the probabilities is a third. Where does a third even come from? I mean, a quarter would have made more sense as an answer. So let's carefully define what's happening here and see if we can work this out. Okay. So here's the definition. I don't need Monte Hall anymore. Definition, let S, so you take any probability space, be a probability space, and A and B, they're subsets of S, which we have this funny terminology in probability. Instead of calling them sets, we call them events. So those are events with the only condition is that the probability of B should be bigger than 0. So B shouldn't be one of these things that never, ever, ever happens. And this is just a definition, so we're not proving anything. This is just a definition. And I'll remind you, I'll highlight that fact. This is just the definition. Okay. So what does this tell us? This thing here, you read it, when you read it out loud, you read this as probability of a given B. So this vertical bar here, it's like the word given. And intuitively, it's asking, what is the probability of A if I tell you that B happened? So let's look at this thing in terms of Venn diagrams. So generically, we have all the possible outcomes. We have A and we have B. And this formula says the definition of this probability of A given B is you look at the probability of A intersect B. That's this piece here. And you divide that by the probability of B. That's this piece here. Okay. And that's just the definition. So how can we interpret this in a way that makes sense to us? Well, forgetting about B for a second, what is the probability of A? Well, very roughly speaking, the probability of A is just how much of S A occupies. Like how much of S does A take up? So that if I pick something at random from S, then the probability that that thing that I picked from S lands in A is basically the fraction of S that A takes up. And in fact, this is true, right? The probability of A is the probability of A divided by the probability of S. And why is that true? Well, that's true trivially because the probability of S is equal to 1. That's what it means to be a probability space is when you sum up over all of the possible outcomes you get, of the probabilities, you get 1. So indeed, the probability of A, another way to think of it is just the probability of A divided by the probability of X. This says, well, what I do is I look at A intersect B, this part, and I divide it by the probability of B. Which you can then say, well, actually, this is like an experiment, the same experiment as before, but I'm only interested in what happens when the thing that I pick ends up being in B. In that case, I'm interested in knowing what's the probability that it's also in A, right? Because that's intuitively, that's what it says. You pick something at random from S, I'm telling you it was in B, what's the probability that it's also in A? That's the probability of A given B. And so this definition kind of makes total sense because you interpret A intersect B as the fraction of B that A happens to have in common. How much of B is A taking up? All right? And that's just the definition. But, so let's test it out, and let's test it out on this problem here. All right. So B was the event, at least one of Anil's children is a boy. A was the event, both of Anil's children are boys. And the question is asking, what is the probability of A given B? And the formula says that that should be the probability of A and B divided by the probability of B. The probability of A and B, so the probability of A and B is the probability of, well, here's A, here's B. A and B only has one element in it. That's this thing. And you divide that by the probability of B. B is this thing. So this is 3 elements out of the 4 equally likely elements. So the probability of B is 3/4. And what's the probability of this thing? Just the thing on top? 1/4. So this is 1/4 over 3/4, which is 1/3. So that agrees with this sort of informal intuition that we got here by saying, well, once you told me that B happened, there were only 3 possible outcomes, and A is one of those possible outcomes. So 1/3 should be the answer. And indeed, this definition, according to this definition, that is the answer. Is that clear?
So the probability of both of them not A given, how do you know it's A given B again?
That's just the definition. This is not proving anything. I'm just saying this is what probability of A given B means. And so we just applied the definition to this word problem. There's A, there's B, and this is what the definition gives, 1/3, which agrees with what we kind of expected. All right, so we're going to save that for later, and now we'll do a few toy examples. Make sure things make sense. So the experiment that we're going to work with for the next few toy examples are you roll 1 6-sided die. So the set of outcomes and we always model this rolling a 6-sided die as a uniform probability space. So there's 6 possible outcomes, the integers 1 through 6, and the probability of any one of those is just 1/6 for each of those 6 outcomes. Okay? So let's take A to be the event. The result of the roll is 3. So I define the event in some plain language way, but that's just meaning that I'm somehow defining a subset of the probability space, and this is a really easy one. In this probability space, what are the outcomes where the result is 3? Well, there's exactly one of them. So the event A is just the singleton set, has one element, 3. Okay? And we know probability of A is 1 over 6. All right, let's let B be the event. The result of the roll is an odd integer. Okay, so B says, I'm only interested in outcomes where the result is an odd integer. And the odd integers in this set are 1, 3, and 5. And the probability of B is what?
1/2.
Yeah. So it's the size of B divided by the size of S, that's this, because it's a uniform probability space, which is 3 divided by 6, which is 1/2. Or go right back to the definition, the probability of B is equal to the sum over every outcome in B of the probability of that outcome. And that sum is 1/6 plus probability of this is 1/6 plus the probability of this is 1/6, which is 3/6. In uniform probability spaces, we usually take this shortcut that we only need to know the size of the set and divide that by the size of the sample space. But if you wanted to do it really slowly, well, you just add up all of the probabilities of the individual events, but you see why that's the same thing, because each of those has a denominator, which is the size of the set S, and 1 on top. Okay. So I roll a die and I don't show it to you, and I say it's an odd integer. Now, you tell me the probability that it's equal to 3. Yep.
1/3.
Seems like it should be 1/3. By this reasoning, 3 possible outcomes. One of them happens to be 3, and there's no reason to think they're not all equally likely, so it should be 1/3. But let's just check it. Probability of A given B is equal to the probability of A and B divided by the probability of B. Probability of B, we know it is 1/2. The probability of A and B, that's the probability of what's A and B. A is the set with only 3 in it. B is a set that has 3 in it, so the intersection of those two sets is just 3, and so we get we get 1/6 divided by 1/2. This 2 goes up, this 6 goes down. That's 2/6, which is 1/3. So indeed, the intuition was right there. Yeah? Yep.
Can you maybe reinterpret conditional probability, like instead of saying the probability of, like when you're saying the probability of A and B, it's within the space S, but can you like maybe consider if the set B was its own space and expand that and then like,
I mean, that's basically what you're doing. So another way to think of it is, I'll just do the experiment S, but if it gives me something that's not in B, I'll throw it out and do the experiment again. And then the first time it gives me something that is in B, then that's really a new experiment where all the outcomes are only the ones in B. So it really is, you're running an experiment where the only possible outcomes are those in B. It's the whole universe of possible outcomes. So it is expanding to be the whole thing, and A intersect B is the part of that that includes A.
the main difference being that like you wouldn't have to take the probability of S into account, like you see in the previous example, the 4 divided out.
Yes, but you have to be a little bit careful. All of this works really well in uniform spaces, and we'll see it shows up all of the time. We get, in uniform spaces, every probability is something divided by the size of S. So that means the probability on top, the probability of A is going to be something divided by S. The thing on the bottom is going to be something divided by S. And so those two divided by S's cancel out. But that's only true in uniform probability spaces. In other probability spaces, the probabilities can be whatever you want, and you don't always get this nice cancellation. All right, that's clear. So here's another one that should be trivial. What's the probability of B given A? What does that mean? It means I'm telling you that I rolled a 3. What's the probability that I rolled an odd number?
1.
Seems like it should be 1, right? I mean, if I told you it's a 3, then that's definitely an odd number, so it should be the case. But let's just test the definition. So that should be the probability of B and A divided by the probability of A. That's just the definition of conditional probability. What's B and A? B and A is 3, right? That's the common intersection of B and A. And what's A? Well, A is also 3. So this is 1/6 over 1/6, which is equal to 1. Good. 1 better have been the answer there, otherwise there's something really wrong with the definition. How do I know what the probability of A was? Because I computed it back here. A was the result of rolling a die, and I mean, is the event that I get a 3, and that happens with probability of 1/6.
Okay, sorry about that.
It's okay. And really the picture here is the following. I told you that I was getting A, and I asked you what's the probability given A that I'm in B. This is what the Venn diagram looks like, right? Told you I'm in A, that implies you're also in B. Let's take C to be the result is a prime number. What are the prime numbers in here? What are the prime numbers in here? 2, 3, and 5. And let's ask for what's the probability of C given B. So I told you that I rolled an odd number. What is the probability that it's a prime number? So what's your guess? Yep. 2/3, because I'm telling you that it's odd, so that means it's a 1, 3, or a 5. What's the probability that it's prime? Well, there's 2 primes in here, so the guess should be 2/3. Quickly check it. So that's the probability of B and C divided by the probability of B. Probability of B and C is the probability of the common intersection of B and C is 3 and 5. Those are the primes that are odd. And the probability of B is, we already figured that out, it was 3 out of 6, or 1/2. And so we get 2 out of 6 divided by 3 out of 6 is 2/3. Everything seems to be proceeding exactly as we expected it. No big surprises there. And yeah, if we wanted, we could do, well, let's do one more stupid one. So if this is what we call B, then that must mean that not B, the complement of B, is, if it's not odd, the result is even. And the even outcomes are 2, 4, and 6. And what if I ask you the probability of C given not B? So I roll the dice, it comes up even. What's the probability that it's prime? Yep. So it's going to be 1/3. Why is that? Or intuitively, why is that? Because these are the even outcomes. Which ones are prime? Only one of them. So there's 3 of them and only one of them is prime, so we expect that it's going to be 1/3. And if we do it carefully, so this on the bottom, not B is 3 out of 6. On the top, C intersect B is 2, right? There's only one prime, even prime number, and it's 2. And so that is 1 out of 6 divided by 3 out of 6 is 1/3. That checks out. All right. And so here we did probability of C given B and probability of C given not B. Notice anything peculiar about the answers? They add up to 1. Okay? And that's not an accident. That's always true. So there's a handy result which says that the probability of A given B plus the probability of No, I'll leave that as is. Oh, no. This is not an example of this, this particular phenomenon. Not A given B is equal to 1. I mean, here's a short proof of it, but the proof is better explained by picture. Okay, and the main point is really what is this thing asking about? Here's A, here's B, here's A and B, here's not A and B. So if I add up all the probabilities inside of here and all of the probabilities inside of here, I'm just adding up all of the probabilities in B, right? I mean, I'm just adding up the probabilities of all the outcomes in B, just splitting it by adding these ones first and then these ones. So that means here's me adding up all of the stuff in the intersection of A and B. Here's me adding up all of the stuff in the intersection of not A and B. So that whole thing has to add up the probability of B. But then we're dividing by probability of B. So the proof is just apply the definitions and then notice that the stuff in here plus the stuff in here that's a partition of B into two disjoint sets. Or if you prefer to think of the intuitive version is I do the experiment until B happens, and then either A happens or A doesn't happen, but those two things certainly have to add up, those two probabilities have to add up to 1 because they're mutually exclusive. Okay, so now comes the surprise. Anil has 2 children. All right. Looks like this so far. So knowing only that, you would think this is the probability space. But I'm going to tell you something about his 2 children. One of Anil's children is a boy who was born on a Sunday. Okay. All right, so yeah, one of Anil's children is a boy. That looks just like this, and then you told me some other stupid thing that he was born on a Sunday, but I don't care about that, because I'm about to ask the same question. what is the probability that both of Anil's children are boys? What's the answer? Yeah. 1/4? It's not 1/4. Yeah. It sure looks like 1/3, right? We worked out here, same statement, Anil has 2 children, at least one of Anil's children is a boy. What's the probability that both the children are boys? That's 1/3. Anil has 2 children. One of Anil's children is a boy who was born on a Sunday. What's the probability that both his children are boys?
Half.
Half? No, it's not a half. I mean, this must be the same thing, right?
Well, over there's at least one. So what?
So we've got a, oh, sorry, at least one. Same statement. Not exactly one. At least one. So everything reads the same except for that was born on a Sunday. All right, so we think it's a third, but we can't know that until we apply the definition. So, unfortunately, that extra thing that you told me about Sunday complicates matters because now somehow the space doesn't involve just the sex of 2 children, but it also involves the days of the week that those 2 children were born on. So it's going to give us a more complicated probability space, but surely it's going to be, I mean, yeah, we'll just get some bigger numbers, but everything will cancel out. In the end, it'll still be 1/3. So let's look at the probability space. It's a set over here. The probability space was that the elements had 2 things, sex 1, sex 2. And either of those could be boy or girl. That's how we got 4 things. Here I have sex 1 and day of the week 1 and sex 2, day of the week 2. So first child was a boy or a girl and was born on this particular day of the week. Second child was a boy or a girl and was born on this particular day of the week. So let's define the days of the week. That's Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So that size of W is equal to 7. And again, I'm going to assume this uniform probability space here, that each one is equally likely, I mean, there's all of these possible outcomes, we'll figure out how many of them, but that each of the possible outcomes is equally likely. So what is this set? Sex 1 and sex 2, they come from the set boy-girl, and day 1, day 2, they come from the set W of days of the week. That's the set of all possible outcomes. So how many possible outcomes are there? How many choices for the sex of the first child? 2. How many choices for the day of the week of the first child? How many choices for the sex of this child? 2. And how many days of the week for this child? 7. So the product rule says that the size of the set S of all the possible outcomes is 2 times 7 times 2 times 7. Or if you like, it is 14 squared. All right? Okay. So we've got these two events. This is the event that we're going to call B. This is the event that we're going to call A, or the event A is both Anil's children are boys. And the question was asking us, what is the probability of A given B? And we all seem to think that it's 1/3. All right, so that means we have to carefully write out for this. This is the probability of A and B divided by the probability of B. So let's take a look at maybe the easier one to compute is the probability of B, or this event B. So this is, both of them are boys. So what does B look like? Well, B is a set. It's a subset of S, so its elements have 4 parts. And those parts look like this. There's a boy, and then there is a day of the week that the first boy was born on. And then there's a boy, and then there's a day of the week that the second boy was born on. And, well, there's no options now for the sexes. They're both boys. So the only options are for the days of the week. And the days of the week can be, no, that's not even true. Let's be more careful. We have to be really careful with B. So one of the children was a boy. So that's A that looks like that. One of the children was a boy who was born on a Sunday. So what does that look like? That could be, first boy was born on the Sunday, and then there was a child. Second child was born on some day. And those two, the sex of that second child could be a boy or a girl. And the day of the week that second child was born on could be any day of the week. Or maybe the first child was born with some sex on some day of the week, and then the second child was a boy born on a Sunday. And that's for any sex of that first child being a boy or a girl, and any day of the week of that first child being in W. So that's the set B. It consists of everything where the first child was a boy born on a Sunday, and everything where the second child was a boy born on a Sunday. So you agree? That's what, when I tell you one of his children was a boy born on a Sunday, that means it comes from this set, the union of these two sets. And let's take a peek at A. A is the one that consists of two boys born on some day of the week, another boy born on some day of the week, and that's for D1, D2, and any day of the week. That's the set A. Both his children are boys. Doesn't matter what day of the week they were born. All right, so we need to know a couple of things. A and B and the probability of B. Let's take A and B, see what that is. So B says that one of the children was a boy born on a Sunday, and A says both of them were boys. So what does that look like? So in here, they're both boys because they're in A, but one of them was born on a Sunday, the other one was born on a different day. So maybe the first one was a boy born on a Sunday, or maybe the first one was a boy born on some day, and the second one was a boy born on a Sunday. Day one. Okay, and now it's time to start computing these probabilities. We know what A intersect B is, we know what B is, we need to compute their probabilities, which means we need to compute their sizes. All right, which one should we do first? A and B or B? All right, let's try. So remember the answer here was 1/3. So what's A and B? A and B is the union of two sets. Let's call them X and Y. So A intersect B is equal to X union Y. And therefore, the size of A intersect B is equal to what? Too quick? What's the size of X union Y?
X plus Y minus, yeah, X intercept Y.
Yeah. So the size of the union of two sets, the size of A intersect B is the size of this, so we want to know this thing, and so the size of that is the size of X plus the size of Y. And don't forget, when we do that, we have double counting stuff that is both in X and Y. This is the intersection, right? That's this picture, the principle of inclusion-exclusion. We have X, we have Y. We would like to know, no, that's right. That's right. X union Y. We'd like to know the size of X union Y. Okay? And that means we take the size of X, we take the size of Y, but we've double counted everything in the intersection. Okay. All right. X is this set here. What's in this set? This is a boy born on a Sunday, another boy, and that boy was born on some day of the week. There's 7 choices for that day of the week. So the size of X is 7. What's Y? A boy born on some day of the week. There's 7 choices for that. And then the other one is a boy born on a Sunday. So that's only 7 things. What's X intersect Y? Yeah. 1. X intersect Y is when you have the first child is a boy born on a Sunday, and the second child is a boy born on a Sunday. There's only one such outcome, right? Why is it 7? Because there's 7 choices for the day of the week that this second child was born on. And in this case, there's 7 choices for the day of the week that this first child was born on. All right. And right now, you should be getting anxious because 13 is a very strange looking number to show up here. if the answer is going to be 1/3, then we'd better get like 39 as the size of B. So we better check the size of B carefully. All right. So let's check the size of B. And B is, again, the union of two sets. Let's call this set X prime. Let's call this set Y prime. So the size of B is equal to the size of X prime plus the size of Y prime minus the size of X prime intersect Y prime. Okay, X prime, what do we got here? We have one child, we get to pick its sex, and we get to pick the day of the week that it was born on. There's 2 choices for the sex and 7 choices for the day of the week. So that's 14 options, right? So X prime has size 14. Y prime, same story, except now the first child we get to pick its sex and its day of the week that it was born on. 2 choices for the sex, 7 for the day of the week. So that's 14. And what about X prime intersect Y prime? Well, X prime intersect Y prime. If you're in X prime, that means the first child was a boy born on a Sunday. And if you're in Y prime, that means the second child was a boy born on a Sunday. There's only one outcome like that, right? That's only one thing in our whole space. So again, we get a -1. And this is 27. And now we should be very concerned that we're not going to get the answer we expect. Where can I finish this? Probability of A given B is equal to the probability of A and B divided by the probability of B. This is equal to the size of A and B divided by the size of S. This is equal to the size of B divided by the size of S. The size of S doesn't matter because it appears on the top and the bottom, so all that matters is the size of A and B divided by the size of B, which is 13 over 27. And then you think, oh yeah, of course, that's 1/3, right? No, it's not. So, if one of Anil's children is a boy who was born on a Sunday, the probability that both his children are boys is 13 out of 27. And 13 out of 27 is 48.15%. A little bit less than a half. Isn't that insane? So I didn't trick you here. I didn't make a miscalculation, and there was nothing like that. This is not some sleight of hand trick. This is just the answer.
So why is like the date of their birth matters? Why does it matter? Because apparently it matters.
I don't have a nice, simple explanation, but it's just, I mean, the reason it matters is that there is this sample space of size 14 squared, and the cases where one of the children is a boy born on a Sunday, there's 27 of those, and the cases where one of the children is a boy born on a Sunday and they're both boys, there's 13 of those. So you can try the same experiment with a similar thought experiment, which is, let's say I pick two numbers between integers between 1 and 1,000. And I tell you one of the numbers was 500. At least one of the numbers was equal to 500. What is the probability that they're both even? Then it kind of feels like that should be close to a half, right? If I tell you one of them was 500, and what's the probability that they're both even? Well, that should be a half. The one I told you about shouldn't affect the other one, and maybe there's some problem with that, some double counting, but the only thing you would have to worry about there is when one of them is 500 and the other one is 500. And that seems really that seems really unlikely. So that's what's happening here, because you can think of this set here has 14 squared things, and half of them are even, meaning a particular thing is child is a boy, half of them are odd, particular child is a girl. So the same kind of thing is happening there, but this is not from the statement of the problem right up until the moment when you do the calculation. You would not believe that you're going to get a different answer until you do it. So the moral of today's lesson is, with probability, your intuition is useful to guide you to maybe what you think is the correct solution, but you need to check it by applying the definitions. And if you apply the definitions and it doesn't give you the solution that you thought, that does not mean that the definitions are wrong. That means that the solution you expected was wrong. Your intuition was incorrect. All right, so that's a good place to leave it for today. Yep.